Okay, so today we're going over synthetic geometry. Thanks for reminding me to unmute. Um, and Justin's gonna be the TA. So if y'all have questions,
Afternoon.
yeah. Justin, want to say something or
Nah, all you.
cool? So yeah, if y'all have questions, email the awesome Justin. And so uh, yeah, try not to spam. And yes, we're recording. Try not to spam. Keep your videos off, just like for sake of like people not getting disrupted. And yeah, so occasionally I might ask about occasionally I might ask about like ask a question and ask you to message me. Otherwise, I'm not always checking. So yeah. So first of all, what is geometry about? Okay, geometry, like a lot of people, when you think of geometry, you think of shapes. So what are some fundamental shapes you think about in geometry? And y'all can message me that. Okay, I see circle, triangle, dodecahedron, triangle, 3D shapes. 3D shapes are really cool. Triangle, circle, square, cube, parabola, quadrilaterals, sphere, cylinder. Okay, cool. So these are all very interesting, very interesting shapes. And I think I'll start with probably triangles and circles. Or yeah, I think I'll just be going over triangles and circles. The other stuff, especially the 3D stuff, is really cool, um but I don't think we're gonna have time for that today. And I didn't prepare for that. So let's start with triangles and circles. One thing we can start with is for a circle. What determines a circle? Um, let's see, 3 points. 3 points, no sides, radius. Yeah, no straight sides. It's a curve, definitely a center, equidistant. These are all really good ideas. Okay, so let's see why it's 3 points. So if you have 1 point, there's so many circles that can contain that 1 point. If you have 2 points, well, now you see that you can if you're if you move your mouse around. Oh, wait, so I forgot to share screen. But there. Hopefully that's good. Okay, bad thing is I can't see the chat right now. So oh, actually I think I can. Okay, so yeah, 3 points can be considered as the vertices of a triangle, and every triangle has a circumcircle. Thanks, Ujesh, for adding that. Um, okay, so let's construct a circle. If we have just 1 point, there's so many circles that can contain that 1 point. If we have 2 points, we have all these many circles that also contain these 2 points. But if you have a third point, that's fixed, right? Wherever we move the mouse around, there's no other circle we can make that contains these 3 points. And if we if we have a fourth point, then like the fourth point can be here, it can be here, can be here. But for most fourth points, It's either inside the circle or outside the circle, and very rarely is it actually on the circle. So very one very unique property of certain sets of 4 points is when those 4 points all lie on the same circle. And so, as you know, 4 points make a shape, which is a quadrilateral. I don't know. Yeah. 4 points make a shape, which is a quadrilateral. And so, yes, as some of you pointed out, this makes a cyclic quadrilateral when all 4 points are on the same circle. This is pretty rare, pretty unique. So it's actually a very useful property. And we want to know when are these 4 points on the same circle. And another property of circles, which y'all pointed out, is that it can actually be determined by 2 points, but those 2 points are not 2 points on the circle, but its center and any point on the circle. Or you can specify a center and a radius, say 2, and it'll pop out a circle. You also have this tool on GeoGebra which you can use. But yeah, so two properties of circles that we're going to use are they're determined by 3 points, and those happen to be the circumcircle of the triangle. And yeah, so let's look into cyclic quadrilaterals. So if we have 4 points on a circle, so let's bring back those. Right, my computer's overheating, so let me put something underneath it. All right. So if we have these four points, so 3 points so far, here another point here. If we have these 4 points, actually, so the thing is with circles, putting in the center is actually a pretty good idea. So with 3 points, how do we find where the center is? What property does the center satisfy? Equidistant from all points. Right. So to find the center, we have to find a point that is equidistant from A, B, and C. So far, we yes, Ori, we can use the thing about being equidistant. Yeah, so how do we find a point that is equidistant from equidistant, that's a property between not just 1 point but multiple points, at least 2 points. So one thing is we can find what points are equidistant first from B and C. Okay, so if I randomly put a point like somewhere here, then D is closer to C than to B. If I put a random point here, E is closer to B than to C. So it's somewhere in the middle, right? And so if we put a point like here, then that looks closer to B and C. Like if we draw DB and DC, DB is supposed to be equal to DC. And so what's another point? Another point might be here, another point might be here. These points are all equidistant from B and C, and they end up forming a line, which is the perpendicular bisector of BC. So the center being equidistant from A, B, and C is definitely equidistant from B and C. So the center definitely lies on this line. The center also lies on the is also equidistant from A and B. So it lies on the perpendicular bisector of A and B. And then, let's see, any ideas? Yeah. So, and then finally, it also lies on the perpendicular bisector of A and C. And we see that all three of these lines concur at one point. Right? So when we have just any three lines, or yeah, when we have just any set of three lines, and yes, thanks Justin for pointing that out. GeoGebra is a really cool tool for playing around with geometry if you feel bored or anything. And so if you have any three lines, like one, this one, and like this one, they likely form a triangle or something else. They likely don't concur at one point. So the fact that these perpendicular bisectors of AB, BC, and CA concur at one point is also something special. Like we were talking about cyclic quadrilaterals, this concurrence is also pretty special. And please don't spam the chat. And so the thing is, we assumed that there was a center. We assumed that A, B, C form a circle. So when we can start out with the definition that a circle is determined by a center and a radius, and then we can use that as the baseline definition and then prove that any 3 points has a circle going through. So this is now our hypothesis. Why, and we want to know why these perpendicular bisectors go through the same point. So we know that any two lines go through one point. So what is this property of D, this point right here? Well, we know it's on the perpendicular bisector of BC. We know it's on the perpendicular bisector of AB, so it's equidistant from AB, and it's equidistant from B and C. So AD equals DB, DB equals DC. So it is in fact the center of a circle containing A, B, and C because it's equidistant from everything. And since it's equidistant from A and C, so it's also on the perpendicular bisector of AC. So the thing about this is that the perpendicular bisector, the perpendicular bisector, a point is on the perpendicular bisector if and only if it is equidistant from the 2 points. The 2 points that define the perpendicular bisector. Okay, so now we know that any 3 points has a circumcenter, and now we want to see why what properties of 4 points and now so we found the center, and so we want to see what are some special properties of 4 points. So I think I'll just erase some this stuff so I can draw a circle with a center right this way. And so I'll put 4 points this time on the circle. When do these 4 points lie on the same circle? So one way to see this is by looking at the angles. Okay, so for example, CBD, that's an angle. So this is an angle on the quadrilateral. How does this angle relate to the circle? We know that the circle is defined by A. So let's related to this angle here, CAAD. Now we want to find like how are these two angles related? And so we go back to our starting to our like basically our definition of the circle. And so the definition is that A is equidistant from B, C, and D. So we can draw AB as well. So now we see that since AB equals AC, this segment right here equals this segment right here. So then, so then ABC is actually an isosceles triangle. So this angle right here is equal to this angle right here. So how do we relate it to this angle? Well, we can actually extend AB. And if y'all know, so can anyone tell why I'm extending AB? And please don't spam. Diameter, that's good. So I'm trying to relate the two angles, or this angle to this angle. So this angle right here is equal to this angle right here. So if we do some angle tracing, if we call this thing right here A, and this is A, or X, this is X, this is also X, this is 180 minus 2X, and so this is 2X. In general, you can think of it as the exterior angle. So basically, this angle right here is the sum of this angle and this angle. So this angle right here is 2x. So this is x, this is 2x. And so if similarly, if we call this y, then this is also y because this is isosceles, and this becomes 2y. So this is x plus y, and this is 2x plus 2y. So this angle right here is twice this angle. Well, this angle right here has nothing to do with B, right? So what happens is if we draw CED, this angle, then this is also twice of this angle. So what is the relationship between angle CBD and angle CED? Yeah, as Alina and Erjan pointed out, they are equal. So angle B equals angle E. So if two angles have this property, or if a quadrilateral has this property where this angle is equal to this angle, then they're on the same circle. If E is some other point, like so for all points E, this angle is equal to this angle. But if E was somewhere inside, then what would happen to that angle? If E was like here, then how would CFD, that angle, relate to CBD? Incongruent. So the angle would increase, as Remy said. And so, and similarly, if F was some point out of the circle, then the angle would decrease. Like it's especially apparent here that this angle right here is bigger than this angle. And it's true for all the other points here. And so we won't go over this next thing in detail, but basically if E was on the other side, then it wouldn't be that CED equals angle CBD, right? Like if E was right here, it would actually be, do people know? CBD and CED, how do they relate? supplementary. So I won't go through the proof here, but it's pretty similar. So CBD and CED are supplementary. So two properties um, that tell you a quadrilateral 4 points are cyclic on the same circle is if you find two angles equal, like CBD and CED, or if you find two angles supplementary, like CBD and CED here. And this is an if and only if. So, like if they're on the same circle, then then the two angles are equal. And if the two angles are equal, then you know that because if E was inside the circle, if E was inside the circle by circumscribing B containing B, C, and D, then the angle CED would be greater than angle CBD. If E was outside the circle, then the angle E would be less than angle B. So the only way that we have angle E equal to angle B is if they're on the same circle. So this is an if and only if. So so this is a fundamental property to show that 4 points lie on the same circle. Okay, and now time for a problem. Okay, so why are cyclic quadrilaterals useful? Or basically just a fun thing with cyclic quadrilaterals, but let's start with a triangle ABC, and then let's put some random points on the sides, D, E, and F. Okay, these don't have to do anything with ABC in particular. And let's draw the circle containing BDF. Let's also draw the circle containing C, D, and E. What do you think would happen when I draw the circle containing A, E, F? Okay. I'm seeing a suggestion that they might be concurrent. Three-way Venn diagram. Find the midpoint. Okay. Let's see. So the thing with just three random circles is, yes, you would make a three-way Venn diagram. Like if I just drew another random circle here, then ta-da, here's a three-way Venn diagram, circle 1, circle 2, and circle 3. But this just happens to go through A, but this is not the circle going through A, E, and F. Right? Might meet. Yeah, so these are very good guesses. And so we see that if we draw the circle going through A, E, F, they do in fact meet here. So why is that? Yeah, good job. Why is that? Miquel? Yeah, so some of you know the problem I'm talking about. So basically, we want to show that these circles are concurrent. They're at the same points. So the thing is that this point G right here, when we start out, we don't start out knowing that they concur at one point, right? The intersection of two things forms a point. So we can actually, so we know that these two circles intersect at this point G. And one thing is our approach this time can be to say why G lies on the circle circumscribing AEF. Because yeah, like if we draw the circle containing AEF first, then we don't know they necessarily intersect both the circles at one point. We might say they intersect, like if it was just any random circle, then it would intersect here, 1, 2, 3, or 4, yeah, 1, 2, 3, 4 points. And we don't want to deal with 4 points, right? So it's better that we just say that these two circles intersect here at point G, and then try to show that, and then we now want to show that the circle going through AEF also goes through G. Okay, so what property do we want to do? Yes, we want to prove that AFGE is cyclic. And someone in Shri is suggesting angle chase. Yes, let's angle chase. And why do we angle chase? Because what we just showed about cyclic quadrilaterals has to do with angles. So yeah, AEF. So ABC is, so just a recap of the problem, we have some random triangle ABC, and then some random points on BC, CA, and AB called D, E, and F. And then we draw the circle centered at B, or going through BDF. We draw the circle going through CDE. And then it turns out the circle going through AEF goes through the same point. And so we first define this point as the intersection of these two circles. And now we want to show that it's on the circle going through AEF as well. So y'all are suggesting angle chasing, and that's a really good idea. So if we angle chase, we want to show that in order to show that G lies on the same circle, we want to relate the angle EGF to the angle FAE. Right, so this has to do with the property we were just talking about earlier with how if you have a point opposite this point J on the circle, then this angle is plus this angle is equal to 180 degrees. So we want to show that these two angles sum to 180 degrees. Well, what do we know about this angle? This angle is easy. This is just A, right? Like this angle FAE is just BAC. It's just part of the original triangle. And I see y'all already got the, like some of you already got the angle chasing. So we want to figure out this angle right here. The only other angles we can relate it to so far are this angle and this angle. We know that these three angles sum to 360 degrees. So we want to find this angle right here and this angle right here. And what we know is how this angle, DGF, let's see if I can annotate. I'm not sure. Okay, so we want to okay, so we want to find angle EGF, and we know that EGF relates to DGF and DGE. This angle relates to the whole triangle by being 180 minus B, because this is cyclic. And then this angle is 180 minus c because this is cyclic. So 180 minus b, 180 minus c. So together they're 360 minus b minus c. So then since this whole thing is 360 degrees, so this right here is 360 minus 360 minus b minus c, which turns out to be b plus c. So how does b plus c relate to a? B plus c plus a is the sum of the angles in the triangle, which is 180 degrees. So that is why. So since angle A plus angle G is 180 degrees, we do have that these three circles go through the same point. That these 4 points lie on a circle, and so these 3 circles, if we define this circle as the circle going through AEF, they concur. Right? This is Miquel's theorem, I think. And let's see now. But here's another problem. So this problem is not just with any triangle, right? Like this problem is within isosceles triangle, but hopefully it'll also show why cyclic quadrilaterals are so great. So to draw an isosceles triangle, one thing we can do is to start with one side, and then, well, where does the other point lie? So the thing with the other point is that since it's isosceles, it's equidistant from AB. So what we know is that since it's equidistant from AB, it lies on the perpendicular bisector of AB. So one possibility for the third point is here. Then CAB would be our triangle. And the problem is, here's the midpoint. And then, so suppose we have some point E, so that if we draw the angle AED, okay, so that if we draw the angle EAD, so this angle right here, this angle is actually equal to the angle EBC. And it probably doesn't look like it, I guess. I'm not sure. Yeah, so some point E, so that EAD is equal to EBC, those two angles. And then what we want to show is that angle AED is equal to angle BEC. So let's see if I can move this screen here so that I can screen share so that I can annotate. Okay. So okay, so Now we want to show that, okay, so let me just go over the problem. Sorry for the wait, but yeah. So now we want to show that this angle, right here plus this angle right here is 180 degrees. Now, how do we do that? One thing we can think of is, well, how do we define AED? How do we define BEC? They seem like very angles that don't have to do with anything else. Like, for example, EAD, if we look at, or AED, if we look at D, what happens is, um, what happens is this D, we didn't need to use it before. The condition that we had about E, that angle EAD is equal to angle EBC, we could have just as well said angle EAB is equal to EBC. So we somehow have to use this property right here that D is the midpoint of AB. So this angle AED is a very special case. We want to relate it to some other angles. Right? And one thing we know about how to relate it to other angles is we can draw, if we draw the circle containing AED, then what we have, move it down a little. But yeah, like if we draw this circle containing points E, A, and D, then we can figure out how angle AED relates to other angles because of the property of cyclic quadrilaterals. So what points do we see that might be of use, that might come in handy here? With respect to that relate to angle AED. So we know that angle AED is the same as the angle of any A something D for any something, some point here. And it's also equal to 180 minus A something D for any something here on this part of the circle. Any part of the circle, and those, it doesn't really matter that we have that 180 minus in the equation, right? So one point we notice is this point right here. That might come in handy. Another point we might notice is this point right here. Another point we might notice is this point right here. All these intersections that might come in handy. It turns out that what we're going to use is actually this point H. So I'll just redefine this point H, right? Or now it's F right here. So what we know about since A, E, D, F are all on a circle, these 4 points, is that AEF plus AFD is 180 degrees. And I'm not sure what book you're talking about, but yeah. So AED plus AFD is 180 degrees. So AFD is 180 minus this, which is telling something. We want 180 minus AED to be angle BEC because we want these two to add up to be 180 degrees. But now we have these two adding up to be 180 degrees. So this angle is apparently supposed to be equal to this angle. So how do we do that? how do we relate angle AFD to angle BEC? One of the ways we can relate it is by renaming. Now that we have this angle AFD that is actually the angle between these two lines, AF and DF is actually CF, we can get rid of this D. We don't see this point D anywhere else in the problem. So now we want to show that angle AFC is equal to angle AEB. And now how do we do that? So the angle AFC, because one thing we might notice is because this triangle is isosceles, angle AFC is equal to angle CFB, this angle. So this angle right here. And so what we want ultimately is to show that this angle is equal to this angle. How do we show that? So how do we show that angle BEC is equal to angle BFC? What we know already is angle BFC is equal to CFA, and CFA is equal to CFD, or AFD, which is 180 minus AED. So yes, as Sri pointed out, we want to show that CEFB is cyclic. Okay. So how do we show that CEFB is cyclic? Now we can bring in our original property that we were talking about. So what we had is angle EAD or EAB is equal to angle EBC. And yeah, so angle EAD is equal to angle EBC. And we want to show that CEFB is cyclic. So since EBC is one of those angles in the condition, so this angle right here is one of the angles in the condition, we want to show that the other angle in the condition is equal to EFC. And how do we show that? Well, we already defined F to be on this circle, right? So if we draw in EF right here, we have that angle, we are given that angle EAB is equal to angle EBC. And so angle EAB equals angle is, we can also say it as EAD. And since we defined F to be on this circle, so it's actually also equal to this angle, EFD. And angle EFD is also, we can rename it as EFC because D is on CF. And then so EFC equals angle EBC. So then CEFB is cyclic. So we have, so that's it. That's what we reduced the problem to. If you want to recap why we needed CEFB cyclic, it's because then CEB equals angle CFB, which equals angle CFA, which is angle DFA, which is 180 minus angle AED. Okay. So that was a problem from some Polish not olympiad, I guess. And let me just try to delete everything here. Okay. Another thing we can do with cyclic quadrilaterals is prove things about lines. So here's a particular, here's a cool problem. Starting with triangle ABC again. Actually, I'm not sure we need the circumcircle. Okay, here. So we start with triangle, or yeah, we do need the circumcircle. Okay. We start with triangle ABC. We put any random point D on the circumcircle. And then now we drop the perpendicular lines, D to BC, D to, and yeah, some of you know this is the Simpson line. And D to AB, which, so if we draw the perpendicular from D to AB, it goes through some point on AB here, but for that we need to extend the line AB. Okay, so now we have this altitude here, DE, and then this altitude here, DF, and then DG. What do we notice about E, F, and G? E, F, G are collinear, yes. So how do we show that E, F, G are collinear? So the thing is, we do something similar to before. We do angle tracing, because just as we needed something plus something to be 180 degrees to show that 4 points are on a circle, to have 3 points on a line, we can show that angle EFD plus angle DFG is 180 degrees. Or another way is we can show angle DEF plus angle, or is equal to angle DEG. We'll go by that because then we don't have to say 180 minus something. Another way you can avoid saying 180 minus is by using this thing called directed angles. Okay. And as Sri already pointed out, we want to use cyclic quadrilaterals again. Okay, so what is angle DEF? We want to relate angle DEF and DEG to show that F and G are on the same line going through E. So supplementary, already said supplementary. Well, the thing is, that is if we want to show DFE is equal to DFG. So we can do that as well. DEF and DEG, yes. So DEF and DEG are supposed to be the same angle, but we want to show that. Okay, so what can we do with angle DEF? And Sri said cyclic quadrilateral. So let's find some cyclic quadrilaterals that have to do with DEF. DEF. It seems like it goes through A. So why are D, E, A, and F on the same circle? What did we define last? We defined E and F last. We defined them actually to be, we defined E and F to be so that this angle right here, DEA, is 90 degrees, and DFA is also 90 degrees. So 90 degrees, 90 degrees, this is a cyclic quadrilateral. 90 plus 90 is 180, right? And it turns out that when an angle is, or when an inscribed angle like DEA is 90 degrees, AD turns out to be the what of the circle, the diameter, yes. So we don't have to use that fact now, but what we do know is that DEF, we can relate it to other angles on the cyclic quadrilateral. So DEF is actually equal to D. So it's equal to what angle? DAF. Yes. So DEF is equal to angle DAF. And now we find that DAF, we don't really need F anymore, right? The other angle we're trying to relate it to is DEG, and it has nothing to do with F. So angle DEF equals angle DAF, which is equal to angle DAC. We can get rid of this talk about F all at once. And now we have angle DAC, which doesn't have to do with E or F. So maybe similarly, we can apply something to finding the angle DEG, right? So how do we relate DEG to other angles? Well, so we use cyclic quadrilaterals again because cyclic quadrilaterals are incredibly powerful for relating angles. So DEG, let's draw that one more time. A circle going through DEG so that we can see what other angles it equals. So DEG, this circle, seems to go through B. And so we can verify it again in the same way. DEB, this angle is a 90-degree angle. And then DGB is a 90-degree angle. So DEB plus BGD is 180, and so it's cyclic. So it's cyclic. So we can say that DEG is actually equal to DBG. I'll zoom in because it's getting a little cluttered, but DEG is equal to angle DBG. So, so we got rid of this E. Now, can we get rid of this G? Yes. Angle DBG is equal to angle DBC. So now all we have to show is, well, we know that this original DEF, we got rid of the E, we got rid of the F. We showed that this angle, by cyclic quadrilaterals, we show that this angle is angle DAC. And similarly, we played with angle DEG. Right, so angle DEG by the cyclic quadrilateral DEBG, we found that that is equal to angle DBC. Now, are these two equal? Angle DAC, this angle right here, and angle DBC, this angle right here. Yes, they're equal. Why? If we remove everything, we find that in the very beginning, we define D to simply be a point on the circumcircle of ABC. So yes, it turns out DAC is equal to angle DBC. So because ADBC are cyclic. So these two are equal. So DEF, this angle right here, is equal to angle DEG. So so F and G actually lie on the same line. For example, if we had a why does this, now a question might be, why does this prove that E, F, and G lie on the same line? If we had another point for G, say here, like H, then DEH, we see, how does it relate to DEF? Well, DEH would be greater than angle DEF. So they don't lie on the same, so EFG don't lie on the same line. And if F was somewhere like here, if H was somewhere like here, then DEH would be smaller than angle DEF. So they don't lie on the same line. So that's why to show that EF and G lie on the same line, then yeah, to show that EF and G lie on the same line, all we have to show is that DEF equals DEG. Actually, I'll just move it to another spot. Wait, it's the time 1:58. What are y'all thinking? Do you want to go through another problem, or do you want to wrap it up? Wrap it up, another problem. Okay, I'll stay for those who want another problem. And some of you have seen this before. I'll wrap it. Okay, I'll give a summary, and then I'll briefly go through another problem. Okay, so far we saw that angle chasing and using cyclic quadrilaterals to chase around these angles is very powerful. We saw it solve the Miquel problem. We saw it solve a problem from some Polish olympiad, and we saw it with the problem. Yeah, this is actually the Simpson line. So we saw it solve the Simpson line. So use, like, when you want to angle chase, when you want to like, yeah, angle chase, you can use cyclic quadrilaterals to relate different angles. And now I'll just go on to another problem for those who want to stay. And y'all might have seen this before, but I'll erase these points so that I can use them. Okay, so we start with a triangle A, B, C. And what are some interesting points that are determined by ABC? Orthocenter? Cool. So to draw the orthocenter, we have a perpendicular to BC, and we know that that perpendicular goes through A. We also have a perpendicular to AC, and we know that that perpendicular goes through B. And then finally, we have a perpendicular through AB, and that perpendicular goes through C. And you see here that they actually, if this line goes through C, they intersect. Now, why is that? So that would probably require some angle chasing, some cyclic quadrilaterals maybe. But if we first just assume that, because we can try to go through this problem a little quicker. We get that this point is some point D. So we have three lines concurring at D, three perpendiculars concurring at D. And then let's also mark these 3 points. And just for fun, let's also mark some midpoints. This point, H, this point, I. So the midpoint of BC, the midpoint of CD. Okay, so the midpoint of BC, we can go around marking the midpoints of all the sides. So the midpoint of CA is, we can call it J, the midpoint of AB, or let me do them consecutively. So midpoint of BC is H, midpoint of CA is I, midpoint of AB is J. And then midpoint of DC is K, midpoint of DA is L, and midpoint of DB is M. And so what do you notice? What do y'all notice about all these points? L, J, G, M, E, H, K, I, F. Circle. Yes, it's a circle. So if we choose any 3 points and draw the circle through them, it goes through all these points. How many points? 1, 2, 3, 4, 5, 6, 7, 8, 9 points. This is called the 9-point circle. Okay. And Shreen actually noticed this quite a while ago. So how does why do all these 9 points lie on the same circle? And how do we relate this to other circles we know? So one thing we notice is that it goes through these midpoints, all these midpoints. How do we define a midpoint? Well, if we, a midpoint is so that the midpoint K, for example, is so that DK is 1/2 of DC. So one thing we might want to do is we might want to expand, enlarge this circle so that DK gets twice its length. So let's see what happens when we do that. Oh yeah, I'm actually not sure there's a scale. Yeah, I don't think there's a scale option. So let's just think about it, right? When dk goes to twice its length, dc, then similarly dl goes to twice its length, dA, and then dm goes to twice its length, dB. So that circle, when we dilate it, when we enlarge it by a factor of 2, centering at D, we get the circumcircle. The circle going through D, A, B, and C. Yeah. So now, why does this, to see why this 9-point circle that contains K, L, M, why this goes through E, H, I, F, J, and G as well, we have to see that their corresponding points lie on the circumcircle as well when we enlarge it. So yeah, when we enlarge DE by 2, why does this land on the circle? When we think of, so now we're back to where we started, right? When we think of why something lands on a circle, we have to deal with angles. So that's where cyclic quadrilaterals come back again. We have to show that twice of DE. So when we think of twice of DE, this is actually saying ED equals EN. So this point N right here is actually the reflection of D across BC. And when we want to show that N lies on the circle centered at going through ABC, we want to use cyclic quadrilaterals. So we want to show that DB or BNC, this angle, is equal to 180 minus angle A. Why is that? Okay, so we want to relate this angle right here to this angle. Now we know that BNC is actually a reflection of BDC across BC. Okay, so this angle right here and this angle right here are equal. And we know how this is defined, BDC. So BDC is made of 2 parts, BDE. So angle B and C equals angle BDC. And then BDC is made of two parts. It's made of BDE. So this thing right here, BDE plus CDE right here. And then you see that BDE right here is just 90 minus DBE. And DBE, with DBE, we can get rid of this D and this E. We can just say CBF. And so this is 90 minus this. And 90 minus this in the larger triangle CBF is actually just angle C. So BDE is actually just angle BEF. So BDE is angle C, and then CDE. Similarly, if we look at CDE, it's equal to angle CBA, which is just B. So then B and C is equal to, so then we get that angle B and C is equal to angle B plus angle C, which is 180 minus angle A. So we've showed that when we do actually reflect D across BC and get N, which is actually the same as what we get when we dilate, when we do it's called a homothency, dilate, homothency, similarity. These are all like the same concept. So when we do a homothency centered at D, that takes every point here to twice its distance from D. Then we get, and we bring E to this point N, we get that N is actually on this circumcircle of ABC. We already know that M, K, and L go to B, C, and A. But now it's great that we know that N is also on this circle. And now all that's remaining is to show that this right here goes to a point that's also on the circle. And so how do you do that? Well, actually, now this time it's not a reflection across BC, but a rotation of some sorts. So let's see how we can draw that. Let's see. Reflect about point. That seems to work. So if we reflect D across H, and then we get this point D prime. And this D prime seems very obviously on this circle, but why is that? So the thing is that when we reflect across the midpoint, what we get is the same circle, or the same triangle. DBC is the same as D prime CB. And so this angle, so just as we said BNC is equal to BDC, which is equal to angle B plus angle C plus angle B, which is 180 minus A. We get that BDC is also equal to 180 minus BDC, or BD prime C is also equal to angle BDC, which is also equal to angle C plus B, which is also equal to 180 minus A. So this angle right here is also 180 minus A. So this point, both lie on the big circle. So when we know that like that twice of all these points, where these points end up on the big circle. So again, we can do reflections of all these points. D across J. When we do a reflection of all these points, all these 9 points, we see that they do end up on the big circle. And so when we shrink them, we know that they end up on some circle as well. And this circle ends up being the 9-point circle. And so when we started off this whole lesson with how 4 points being on a circle is really cool, now we end it with a 9-point circle where 9 points end up on the same circle. So yeah, hopefully y'all enjoyed this bit of math. And if y'all are interested in learning more about stuff like this, I might recommend this book, Euclidean Geometry for Mathematical Olympiads by Evan Chin. UGMO. It's pretty cool. And you can also go on Wikipedia. Definitely play around with GeoGebra some more. And yeah, hope you enjoyed. And y'all can look more into the 9-point circle and so on. And see you next time.